The gasoline engine is one of the greatest inventions in human history that still propels us today. But do you ever wonder how it actually works behind the scenes? Well, in today's video, we just happened to stumble across this engine, which we will use to show you not only how the operating theory is, but how things actually work behind the scenes right after this. So before we dig into this engine and find how things work behind the scenes, let's talk about the very basics of engine operation. This is a 4-stroke gasoline engine. Every gasoline engine needs 4 things to run. You need gasoline for the combustion. You need air, or more importantly, oxygen in the air, which is going to help that combustion. And then you need something to compress them. And of course, you need to ignite that mixture using the spark plug. So they would combust and create that power that propels this engine forward. So here is how things will work in theory. This is a 4-stroke engine. That means it has 4 strokes. And those strokes are intake, compression, power, and exhaust. And the way this works is intake is when the mixture of fuel and air goes into the engine, and then the compression stroke is when this mixture is going to get compressed. Here we have the 3 things that happen. When you compress this mixture of gasoline and air, or specifically oxygen, you're going to create that combustion, which is going to create like kind of a gas that's going to come out from that combustion that's going to push and create that power stroke. And that's what's actually going to start rotating this engine. And then all this combustion gases that are just sitting there, they exhaust in the 4-stroke, and then we repeat. Now this is for 1 cylinder. This particular engine is a 4-cylinder engine. So this cycle is going to happen for each individual cylinder. And that's how you get that continuous flow. So this is what it's called the firing order. Cylinder 1 is going to fire, then 4, then 2, then 3, and then we repeat. It's just going to keep going. That way you don't have 1 cylinder firing and then we kind of lose our momentum, then the second one, then the third one, the fourth one. No, they're designed to continuously run, so you always have a consistent power band. That sounds all great, but how does this actually happen behind the scenes is where we're going to dig into this motor and find out exactly how that works. So before we dig into how it works, let's label the components, understand what are we looking at here, because this is not one piece, this is multiple pieces, and some folks will say there's thousands of parts to an engine. Not thousands, but there's a lot of parts. Let's talk through them. This is the top of the engine, this is the front of the engine, and that is the back. This part right here is called the valve cover. This is just a cover that keeps the oil inside. That's all it does. It has the oil fill cap, has a few other components. That's all it does. It just covers things at the top. Then you have the cylinder head. This is one of the most critical, most delicate parts of an engine. This is what allows the mixture to go in and go out the exhaust. We're going to dig into it and we're going to take it apart, and you'll see every little part of it. This part is a cylinder block. This is where your compressor is. This is where the pistons live, and this is what actually compresses that mixture, and then the mixture pushes it down for the power stroke, and then it comes up again to push the exhaust, and then as it goes down, it pulls the mixture in. This is not making sense right now, but when we take it apart, you'll see how it does that, and it will all make sense. But let's just cover the parts so you know how they look like. This part at the bottom is called a stiffening case. It's literally just an extension of the engine, just to have that area where the oil sits. And this very bottom piece is the oil pan, and this is what contains the oil of the engine. Now, let's start peeling the layers, and we'll see how this works. Let's start peeling our first layer. This is the valve train. This is a very simple engine. Things get a lot more complicated from here, but we chose this engine for a purpose. This is a dual overhead cam. These are the camshafts, and they are sitting on top of the cylinder head. That's the identification of that style. There is multiple designations. There's single overhead. There is not overhead. There's a lot of different configurations, but this particular one, which is the most common one in modern cars, dual overhead cam. So, what is a camshaft? All this does is it synchronizes the strokes of the engine. When are we going to allow that mix of air and gasoline into the engine? And when are we going to allow that exhaust to come out? So I'm going to turn this engine as if it was running, and I want you to watch what things are doing here. Do you notice this particular peak? This is called a cam lobe, and it is kind of in a droplet shape. And the reason for that is every time this high, like pointy part goes down, it opens something called a valve. Every time a round part goes over it, it is closed. Now these valves are what's going to open to either let the gasoline mixture and air mixture in, or it's going to, on the other side, is going to let the combustion gases go out in the exhaust. And when they are both closed, we are in the compression stroke, because you have already the mixture inside the combustion chamber, which we're going to look at in a little bit, and you are compressing it. So if you have one of the valves open, it's just going to come out, nothing will happen. So you have three stages of this. They're either open on one side, closed on the other, open on one side, closed on the other, or they're both closed. Now, there are cases, we're not going to get too complicated into, there are cases where this is delayed and that's delayed. We're not going to get into that. We're going to keep things simple because they're actually a lot more complicated. So, here's what's going on in this entire picture. Each cylinder in this particular engine, it's 16 valve engine, 4-cylinder. You have 4 valves per cylinder, and this is the separation of the cylinder. Do you see how you have 2 lobes here and 2 lobes here? This is the intake side and this is the exhaust side. The camshaft will always spin half the speed of the crankshaft. So if you're driving your beautiful car at 1500 RPM, this is spinning at 750 RPM. This is how this works. The camshaft will always spin slower, and what this does, the way the lobes are orientated is according to the firing order. Well, we did the 4 strokes here, but at the same time, the 4 strokes are happening somewhere else and somewhere else and somewhere else. They're in different phases of each other. But we're going to actually focus on one cylinder only. Right now, both of them are closed, and this is the beginning of the cycle. Watch the cycle on the intake side first. This is the intake. I'm going to turn the engine. Do you see how the intake is opening? The pointy part of the lobe is down. Now we are taking in the intake mixture. We're going to continue. This part is actually the compression. Do you see how they're both closed? Pointy part here, pointy part here. The compression is happening. And then, watch what's going to happen here. We're going to open the exhaust valves. Now we're letting that gas out. And then as we let it out, we're getting ready to start the cycle all over again. Do you see how that works? But how is it actually doing that? See, this part right here, this is called a timing chain. You have 2 styles in engines. You have either a timing chain, a metal chain that synchronizes everything, so all these 4 cylinders would do what they're supposed to do at the correct time, or you have a timing belt. This particular engine is a chain. We're not going to get too much into that part of the design, but let's see, how does this actually happen? What is this pointy part? What is it actually pushing against, and how is that mechanism working? And in order to do that, we're going to remove all the chain, we're going to remove the camshafts, we're going to look at the camshafts outside, and then we're going to remove the cylinder head, which contains the valves that do this, and see how that works up close and personal. So let's take a look at the camshafts up close. Do you see those lobes? That's how these look like. You see how they're not in the same orientation because each one corresponds to a certain phase in that four-stroke for that particular cylinder. So they will not be the same, and they are engineered that way to work in that order. Now let's take these out. Look at the area where they sit. So this camshaft is just a piece of metal that is spinning. I mean, if you're driving your car at the highway, 3,000 RPM, this is spinning at 1,500 revolutions per minute. That's a lot. And how do you not have this metal piece and this metal piece get destroyed? Here's how that works. This is called a journal. This part has a hole in it. See that little innocent looking hole? That's actually an oil hole. So what's going to happen is oil will come out to this tiny little hole, put a film of oil on top of this, which then is going to end up here and on this little cam cap that sits here. That film of oil here will actually prevent wear between these two metals because they will actually not be touching each other. They will be riding on a thin film of oil here that keeps this lubricated, cools it down, and not allow this metal to metal contact. That is pretty cool how that works. Now we talked about the cam lobes pushing down. Well, what is it pushing down on? Let's just take this cam out of the way. Let's take a look. What is it pushing on? Because this just looks like a flat surface. But see, the thing with gasoline engines is they warm up and they cool down. And what happens to metal when you warm it up? It expands, you cool it down, it contracts. So if we just put this cam here, what's going to happen when this metal surface heats up, expands, this metal surface heats up and expands, and they're just going to be fighting each other? Or when this metal surface cools down significantly and this metal surface cools down significantly and they shrink, well, there's going to be a giant gap. So how is that going to work? That is called valve clearance. It is something pre-calculated by the engineers that designed it, where we want this valve clearance not to be too tight, where this valve will potentially be pushed down all the time and open, and we can't have our power stroke anymore, where both of them are closed. Neither is going to be super loose, where we're not going to be able to open our valve all the way and allow that beautiful gasoline and air mixture to go in, or the exhaust to go out. So they set it as specific clearance that allows for both cases to work. This is called a manual valve clearance engine, and this particular engine is that. More modern engines and more sophisticated engines will have automatically adjusting valve clearance. What they'll do there is they'll have a little plunger that is oil pressured. When the gap gets smaller, it'll ease up to allow for that expansion. When the gap gets big, because the engine is cold, it's going to pump up and take that gap between the cam lobe and the valve. But this is actually not the valve. And this is a little bit of an older design on this particular engine. This is called a bucket. And the way you adjust valve clearance on this particular engine, do you see the inside of this bucket? This is actually a numbered bucket. So the distance between this inside and the outside can be changed by the number that is stamped on this bucket, which is just the distance. You can see that number. I don't know if it's clear inside. There's a number which corresponds to a certain thickness of this. But this is the actual valve that this is pressing, which in turn the camshaft lobe is pushing on to open and close the valves. That is the most basic operation. But wait a second, what is this little fancy looking thing here? Let us take the cylinder head out of this engine, take a valve out, and let's just take a look at it and see how that looks like. Now here are the valves we were just looking at. These actually look like this inside. This is a spring. So remember when we were looking at the cams, they push on this. Well, what's going to return it to close it? This is called the valve spring. It's just a spring that has a specific tension, depends on the engine. So it would return the valve to the closed part. And speaking of the valve, this is a valve. It's fully assembled. And here's what holds this valve in place. If you look at the tip here, there's this retainer. And then inside this retainer, there's actually two little locks. I'm going to get them out. These tiny little locks, which are called keepers. What these locks do, if you look at the tip of the valve, you have this little groove. These also have a tiny little groove that will go right there and get locked in that groove where it's not going anywhere. And then this retainer will come up and lock it in place. And that's what you're looking at here. These are all locked in place. Here's how that spring looks like. And here's how the valve looks like. Now here's the interesting thing about these valves. This is called the stem. This is the valve face. This is actually facing the combustion chamber, which we're going to look at here, the top combustion chamber. In this area, you have oil. In the combustion chamber, we do not have oil. So in order to keep that oil away from going into the combustion chamber through this, around the stem, there's actually a seal that sits behind each one of these valves. And we'll show you a little clip of that seal, how it looks like sitting down and then outside. These seals are called valve stem seal. It's the seal that seals the stem of the valve to not allow oil to go into the combustion chamber on top of the valve. Now let's talk about valves. Intake and exhaust valves are not the same. Usually the intake is larger. If you have a car, and in case you hear this, that is direct injected only, and you have carbon buildup on the valves, they're actually going to build up carbon here, not here. That's a common misconception about cars, folks. All engines will build up carbon here, including this one. That's just normal. Not excessive amounts, but this does have residue on it. You cannot clean this with a little can of magic stuff that you put in the tank or the shop chart. You cannot clean this. This is normal. The minute you run the engine, there will be some carbon. That is normal. But when carbon builds up here, you're going to start obstructing things. Eventually this valve will stick and won't be able to be closed by the spring, and we have issues. Or it'll be completely plugged where you cannot no longer allow that mixture to go through. I just thought I'd say this now. Some carbon buildup here is normal. Excessive carbon buildup here, we have problems. Why is this valve clean? And why do direct injection engines build up carbon here? See, the way the port injection work, it actually sprays gasoline in an area of the runner leading up to this valve. So gasoline and air will come together, touch this valve, go around it into the combustion chamber. While direct injected engines, they will only have air passing through here and then gasoline being sprayed directly inside, not before this guy. So what ends up happening over time, there's something called blow-by that will build up that carbon here because there's no gasoline passing through here and washing it off. That's why direct injected engines build carbon. Welcome to the top combustion chamber. This is the other side of the cylinder head. These are the valves that we were looking at that were basically this. This sits right in here. This is when it's open, and this is when it's closed. So every time this comes up, it allows either, if it's this side, which is the intake side, it'll allow that gasoline and air mix to come in. If it is the exhaust side open, it'll allow things out. And what is dictating what's coming in and out is a part where we'll talk about in a little bit. I just want you to see this part. Now, one thing we will say right now, this just looks like, to the average person who is not into cars, not into this stuff, this just looks like an oily mess. Just random parts, dirty, oily, greasy, grimy. This is the most delicate, most highly precisely engineered part of the entire engine. Everything else is nuts and bolts. This is where the magic is. Because do you see this valve? This valve actually has a surface where it seals on, because this needs to seal. And the part right here is called a valve seat. This is a very precisely machined part. So is this one. So when these two sit together, like so, they're actually sealing the combustion chamber. So this is not an oily mess. And the other thing is, this surface itself is a very precisely machined part. Because wait a second, we have this part and we have another part, and the combustion is happening here in this area for each cylinder. Well, how are we going to seal this compression from going outside? This is where your head gasket is. You'll hear blown head gasket, leaking head gasket. This car has a bad head gasket. Most people talk about this, they don't even comprehend what a head gasket does. As the name says, the head gasket is just a gasket. It sits right here, and it seals between the cylinder head and the cylinder block. We're going to talk about the cylinder block in a little bit. But here's what usually happens. You overheat this engine, for example. That's the most classic case. What's going to happen is, this is a precisely machined surface. This will heat significantly. And if you notice, these openings, these are actually cooling jackets. They cool this area. So coolant will go out of here into this area and then into the block. And that's how coolant is going back and forth. Well, when you superheat this, aluminum tends to warp when you heat it, meaning it's no longer flat. So this will open, and then you will have multiple of things will happen. Either you will mix oil, because there are oil passages here as well. Some of these passages are oil passages. You will mix oil with coolant. That's the most common thing that people will think it happened. But it's not always the case, because if you actually break the area between two cylinders, you will have all kinds of issue, because you will bleed combustion from this one into this one, and this one is not ready, and it'll just become a mess. And the last thing that is common, this gasket corrodes and starts leaking outside, either oil or coolant or both. These are some of the things with cylinder heads problems for modern engines. Now, if this is warped, you must machine it or replace the cylinder head if you're not able to machine it due to tolerances. This needs to be a perfectly flat surface, and we're not talking, oh, I've passed my hand over it. This is like machining style, perfectly flat. Having said that, I'm gonna put one cam, I'm gonna turn it. It's gonna be a little difficult, so you can see how these valves actually work when the engine is running. Let's watch these valves, not open and close, dance, because this is beautiful. Look at this. Isn't that something beautiful? So this is actually cylinder number 1, 2, 3, 4. I'm going to go through an entire cycle until we open 4 again. See if you can pick up the firing order from this. Pretty cool, right? How these valves open. You notice they're both opening together. So if we do the math here real quick, these are 16 valves. This is a 16 valve engine. 2 valves for the exhaust, 2 valves for the intake, so 4 valves per cylinder. And this opening right here is actually where your spark plug is. That's what ignites the mixture so we can create that beautiful combustion. If you had a direct injected engine, you will have a second hole, just like this one, where the direct injector is somewhere either here, or sometimes it'll be right here, and the spark plug will be in a different position, but somewhere inside this cavity right here. Now, having met the upper combustion chamber, let's go see the real magic of gasoline engines, which is the other part of the combustion chamber, cylinder block. Welcome to the combustion chamber, which is actually this one. It's actually not the entire depth of this. I hope you can see this very clearly. It is just this area and the top of the cylinder head. I'll remind you how that looks like. Let me spin this and watch how this works. This is the piston. There's 4 cylinders. 1, 2, 3, 4. Here's what's going on here. And the best way I will be able to describe it. This is the compressor part of the engine. When this piston, watch these two, when they go up, they are compressing. When they go down, they are pulling. So here's how this is going to work for our 4 strokes. Let's start with the first stroke, which is the intake. We want to naturally pull that mixture of air and gasoline into the combustion chamber. We're going to have this piston go down. So what it's doing is creating a suction. It's going to pull the mixture inside this area. Then we're going to want to compress that mixture and ignite it with the spark plug. So what it's going to do is it's going to come up and start compressing. As it reaches its peak at a specific position, the spark plug will ignite this mixture. So the mixture will burn. As it's burning, it's going to create like a gas, and it's going to push this piston down. And then because we have 4 cylinders, let's talk about it this way. This piston has ignition. We have combustion. It's going to push this piston down. Then this one has ignition. It's going to push it down. Then this one has ignition. It's going to push it down. Then this one has ignition. It's going to push it down. And then this one is going to have ignition again. It's going to push it down. And that's how your engine will just keep turning and turning and turning and turning nonstop. Now, this is the beautiful part of this. This piston is in the intake stroke. It's about to start pulling the components in. This one just had combustion, so it's going to get pushed down. Now these 2 pistons, one of them is in its ignition cycle, one of them is about to start the intake, and that's how this firing order works. It is beautiful how this works. You see how this is, when you spin your engine at 3,000 RPM, or you are 18 years old, you are an adult and you are racing your car down the street, which you shouldn't do that on public streets, and you're revving this engine at 6,000 RPM all the time. Every minute, which is 60 seconds, this crankshaft will do a full rotation, which the full rotation is this piston going up and going down back to the same position 6,000 times every 60 seconds. This looks like How do engines last? This is the moment where we say, thank you, engineers, for figuring this out. Look, mechanics and engineers usually don't get along, but we have to be truthful. They know what they're doing. This is how these engines are designed to run and run and run. Here is the important things. This, which we're going to take it out in a little bit, and you'll see it up close and personal, is sealed. There is 3 rings, or piston rings, that are sealing this chamber. And for you to get a better understanding of really what's going on, like how does this effect work, let me do a small demonstration. We are looking at 2 cylinders. I hope you can see the outline of them. We got them covered up with tape, just so you can see how they do this, so you can picture it. Every time the piston goes up, it's going to create compression. Every time it goes down, it's going to create suction. So watch as I turn the engine, what the tape's going to do. See how this one came up? This was compression. Now it's coming down. This one is coming down. Now it's coming up. Funny sounds it makes. This is actually the compression. Watch this one when I push it very hard. That is the compression, and this is the suction effect. Actually, it becomes really difficult to turn this engine because of the obstruction. Eventually, it actually blew. Do you see how it blew the tape? That's how strong this compression is, folks. It needs to be extremely strong to do this. Now that we picture how this works, let's talk about a few nuts and bolts things here. This round is the cylinder itself. So the head gasket sits here. This is also a very precisely machined surface, so it would seal on the gasket. Now, in here, there's actually a liner, because this is an aluminum block. If you create that combustion on an aluminum block, you will immediately fire a hole through it, and it'll wear down with the piston rings going up and down on it. So this is actually a steel liner. Now this particular engine is out of a Toyota. Some engines, this liner can be pulled out and replaced. This one cannot, because the way they cast this aluminum, they put the 4 steel liners and they cast the thing around it, and they are mechanically bonded together so they wouldn't come out. So you cannot really replace these. But the wall of the cylinder has a specific machining to it, and that is called a crosshatch pattern. And keep that in mind, because we're going to talk about this once we talk about the piston rings. This area, this cavity right here, this is where coolant is to cool these down. Because remember, combustion creates a lot of heat, so you have coolant all the time here, cooling it. And then you also have oil passages around it, because in gasoline engines, coolant cools, oil cools as well. Most people forget that part. Having looked at all this and this beautiful thing turning, how do this entire thing work, and why do these come up and these come up together? How does this work? Let us flip this block and look how this entire thing works, and then we will take one of these pistons and tear it completely apart so you can see exactly how this creates this compression or pressure and the suction, and how does this exactly work. Welcome to the back of the cylinder block. This is where the magic happens. Let me spin it so you can actually see how this goes. So what we were looking at from the other side, you see that piston right there? See how it's going to come down and go up? This part right here, this is called the crankshaft. This is actually what outputs the output of the engine, not the camshafts, because connected on the other side is whether it's manual transmission, automatic transmission, plain propeller, you name it, it's connected on this side. This side is where your serpentine belt or drive belt will be. This is a harmonic balance. This is where the other side of it is, but this is what actually drives your car this way. It's the crankshaft that drives the car, because every time, remember that power stroke we talked about where the piston gets pushed up, is going to push on this and turn it. And that's what's going to create that output. And that's where the power of the engine is transmitted out. Now, you look at this. This just looks like a random piece of metal. Looks like a museum piece. But let's take a look at the finer details of this. This is a crankshaft. And it's connected. Then it goes here. Then it comes back. Then it goes here. It comes back. And comes back here. But this is actually a separate part. And these are called the main caps. This is what bolts the crank to the block. And these are called rod caps. This is what actually bolts the piston to the crank. Not directly. We're going to take one apart and talk about it. Let me remove one of these and we'll kind of examine it, and then we'll continue from there. This is actually how this piston looks like. This is called a connecting rod. This connects the piston to the crankshaft via this round opening which goes on this. This is called a crankshaft journal. This is where this would ride on. It kind of looks like this when it's connected. So do you notice that this one has also a hole? Remember when we talked about the cam? This is the oil feed hole. And if we look at this, we take this half out. It has actual rod bearings. These are little bearings, and you notice they also have that hole. So here's what's going to happen here. If we have this metal on metal surface just going at 6,000 RPM as you're racing your car, well, this is just going to wear out, and it's going to wear this out, and then everything will just explode. Actually, that's not how this goes. You have a thin film of oil that comes out of here and coats the inside of this and the other side. So they're actually not making contact. They're not supposed to make contact. There's supposed to be a film of oil here that cools these and protects them from wear. These rod bearings, and you'll hear the term rod knock. The rod knock is the knocking sound that the rods will make as they go on the journal here when these completely wear out. Let's do a small demonstration of how that sounds like. Now, when I turn this, you hear no noise. And this is solid. It's not going anywhere. I'm going to remove one of these caps. Note, do not do this on an actual engine. This engine is junk. We are using it for demonstration. I'm going to remove these because this is basically what happens. You see how thin this is? If this wears down, you basically have this is gone. So what I'm going to do here is I'm going to remove them. And then reinstall this. Never use power tool on engine. Remember, this is a non-running engine. Now watch this one. This one is solid. It's not moving. Hear that noise? And watch when I turn the engine. Hear that noise? That noise is a rod knock. Basically, your car will be idling. You'll hear this. Now, eventually, what's going to happen is the bearing will be completely gone. This will start eating into this, and eventually, either this will break and this thing will come flying out and come out of the side, or this, from the hammering effect, this will break in half, rip, and go outside of the engine. Now when you hear the term rod knock, you know exactly what that means. That means this ugly sound. Now here's a cool thing here. You notice we talked about these, but we did not talk about these caps. These are called the main caps. This is what holds the crank to the block. And they also have bearings, because we also have an oil hole right here that brings oil, so we would not have metal to metal contact. Now, something about gasoline engines. Usually, when you have oil starvation, when you run the engine low on oil, you have a problem with the pressure, it's always the rod bearings that will get destroyed before these. I mean, if you destroy a main bearing, we are doing some serious stuff here. Because the way the oil flows in engines, it'll flow to the main caps first, then through the crank, go here. So it'll flow from the block into this, then into this. So if you destroy this, this is long gone. That's how it usually goes. Now, we talked about all this, and you see this journal. This is on the crank itself. I'm going to pull this crank out so you can actually see it in person and see how it looks like. We got our crank ready to come out. One thing I'll say about the crank, this seal, do you see this seal? Let me pop it out. This is your rear main seal that when it leaks, you have to pull the transmission out or pull the engine out, because it literally sits between the engine, and this is where the transmission would be on that side. So this is how that looks like. And with that out, pull this out. And are you ready to say hello to the crankshaft? Very heavy part. That noise we'll talk about in a second. This is how this crankshaft looks like. Isn't this a beautiful piece of engineering that other piece of love will also talk about? Isn't this a beautiful piece of engineering? Just look at this. I will put this in my dining room as like a decoration. I'm a car guy. Maybe my wife will not think so as well. But this is a crankshaft. You notice how it's stepped in a specific way. These are the mains that hold it to the block, which, by the way, here's that other bearing on the other side. You notice these are much heavier duty bearings, that they have a much larger oil passage through them. And then the rods, much smaller. There's 4 of them. This is how a crankshaft is. And this other side of the crankshaft is where if you have a manual transmission, where your flywheel will connect. If you have an automatic transmission, this is where your flex plate will connect, that the torque converter will connect to. And that's where the output of the engine is. Now, when we took this crank out, we had these 2 very innocent looking washers come out. See how much wear they have on them? These are called thrust washers. Now, as you load this crank, every time, you see how it has a little bit of movement? And it's specifically designed for that. Every time you put, like you push the piston down and you have like lateral movement, these are actually going to limit that or hold the crank in place. They are wearable. They do wear with time, but you will rarely see these go out. Some engines, and this is another thing we'll talk about, some engines, these actually sit right here. We've seen cases where one of these or both fall out and they'll end up in the oil pan. And here's what ends up happening. You'll have a very strange knocking sounds that sounds like this. People will think it's rod knock. They'll take the engine apart. They'll freak out about it. They'll think it's a tensioner. They'll think it's a heat shield. It's actually one of these fell out or wore off. This could tear up the engine very quickly. Now that we've talked about this, I'm going to remove this. I want you to observe something. Let me turn this a little bit. Do you see these 4 jets that are facing the piston? This is where the piston would be, right here. These 4 jets are vital to engine operation. Folks, did you know that coolant is not the only thing that cools down engines? It's actually oil. You remember the old engines? They were air cooled, but it's actually the oil that cooled it, and the air helped cool the oil. So these jets are spraying oil directly at the back of the piston to cool it down, because the combustion is happening right on top of it. They are vital to the life of the engine. Some engines will have 2 jets, not just 1, and they're precisely positioned where they spray a specific amount to cool that piston, just so it would not overheat. Speaking of the piston, let's go look at that closely and see how that is a huge, important part of this beautiful piece of machine. Here's a piston. Now let's talk about this, because this, to me, is the magic part. So this is the piston itself, and it does have multiple components to it. Now this is an assembled one. Let me bring one that we took apart so you can see. This is how this actually looks like. So you have a wrist pin, which looks like this. That's not completely worn down. This goes through here, goes through here, and then comes out the other side, and then there's 2 little rings that lock it in place. Normally, they will do this. They have a little bit of movement. That is normal. People have taken engines apart that have no business of doing so, and they look at this and they're like, well, this is making a lot of noise. That is normal. What this allows the piston to do, as it's going up, and then the crankshaft turns direction to come down, it allows it to swing back and forth. This is just a beautiful thing. This is a rod, and the bearing is here, piston on this end. Now here's what can cause issues with these rods. Usually the rods, believe it or not, are sacrificial in an engine. Same thing with the bearing on it, because you want to protect the crank. If, for example, you drive your car through a giant puddle of water and the engine takes in water, the water is going to come here. Now, you can compress air. You cannot compress liquid. And if you get large amounts of liquid here, this will try to compress it and it'll just dead stop. So what's going to happen is this, let's think it's going to do what this does. It's going to literally bend. And when this bends, it's no longer going to make it all the way up, and you'll have all kinds of problems. Or if this seizes all of a sudden and this try and push on it, this will literally break in half. That's what this does. So when an engine threw a rod, that's a term you will hear, this broke and just went sideways, broke the cylinder, and just came out of the side of the engine. That's what an engine that threw a rod through this. But let's get the distraction out of the way, and let's focus on the most delicate part of an engine. The piston rings, which, did you notice that this one just broke? That's actually one of the problems of this particular engine. These piston rings, there's 3 of them. 1, 2, 3. The top 2, and take them out. These are the compression rings. This is what seals this piston as it goes up and down in the cylinder to create that compression. Second one is also a second one that does the same thing. The third one is called an oil control ring. I think this one will not come in one piece, and we'll just rip it out, and that's okay because it's broken. This third ring, which now is in two pieces, do you remember that jet that was spraying here all the time? Well, that oil eventually going to splash and want to stay on the cylinder walls. This scrapes it down as we go. So we would not have oil inside the combustion chamber, which now is going to basically, your car is going to start burning oil. See, we've talked about oil consumption in a video detailing why they do that. Why engines burn oil. It's not these two. These two, if you have no compression in the cylinder because of the rings, these two will be to blame. But if you burn oil, it's actually the third one that does this. So this has a spring. See if I can get it out so you can see it. This spring sits, these are actually two. Now these are no longer two, but these are actually two rings, and this one sits in between them, and it pushes. So if you look here, it's extremely difficult to see it because this is why this engine is used as a demo. There are holes here. Every time the piston is going down, it's actually going to create pressure downwards. And when you have that oil pushed in here, it's actually going to push this ring out and scrape the oil down from the cylinder wall, so we wouldn't leave it there and then burn it. When this gets seized from many reasons, this is one of them, this will no longer be able to scrape the oil down. And then another thing that could happen, these little passages here will get clogged, and then they will no longer push this out, and then nothing happens. Now, let's talk about other things with pistons. We're not get too much into it, but remember that mixture that we talked about of a perfect amount of fuel and a perfect amount of air, which has oxygen in it. The perfect mixture, let's call it in the middle. You can go either way. When you go more fuel, less air, you go to a mixture that's called rich. What the rich mixture is going to do is you're going to dump so much fuel here that it's too much for the spark plug to ignite all of it. So some of it will actually trickle down and come out of the exhaust. That is called a rich mixture. Rich mixtures lower the temperature of the piston. So have you ever have gasoline in your hand? I don't encourage you to do so, but if you ever had that experience, it actually has a cooling effect. And that's what it does when you have a rich mixture. You're going to cool things down, but at the same time, you're going to build up some carbon, because all that unburned fuel is just going to linger, and the next cycle is going to get burned, but it's too much, and it'll leave deposits, and now we have all kinds of problems. The second kind of edge of the spectrum, too much air, too little fuel. That is a dangerous mix, because when you have too little fuel, too much oxygen, you're actually going to cause a lean condition. Lean conditions in an engine are like a torch. That's the best way I can explain it. If you ever used an oxyacetylene torch, you know exactly what I'm talking about. Too much oxygen in a combustion will create a very hot flame that will actually melt the piston. Now, we're not talking about you got a code, small code for system lean, and we're talking extreme cases where the computer cannot control it. It will literally melt this piston, like some of these pictures you see here. It will melt this piston because this piston is aluminum, special kind of aluminum, but it's still aluminum. It's designed to run at optimum operating conditions, not the torch of the lean condition. Let's talk about a few things with gasoline engines that you should know about. The pattern is that it's called crosshatch. If it is lost, the oil rings will no longer be able to clean that surface. That's one thing about them. And the best part is what wears down the crosshatch is the oil control ring when it seizes. It's supposed to move as we go, and when it doesn't, it just starts wearing in one area and you have loss of crosshatch, and we no longer have the ability to scrape that oil down, and the engine starts burning oil. Oil, by the way, of course, oil is derived from the same place, crude oil. So you start to have elevated levels of hydrocarbons, and eventually this causes all kinds of issues. Believe it or not, engines that burn oil actually run slightly cooler than engines that don't. And the way you know an engine burns oil, if you're like, take the spark plugs and send the camera in, easiest way to know, of course, if you have cylinder wheel damage, well, you know that that engine potentially burns oil. But there's one telltale sign, which is reading the piston. See, this one has so much carbon that this is a different case. But if you look at a piston, you look like a 4-cylinder engine. If you have a coolant issue getting in here, see, coolant is a mixture of water and ethylene glycol in most cases. Ethylene glycol is the part that causes the antifreeze part, and water is just water. It's to cool things down. If you have water here, or coolant in that case, that water will steam up. It'll become like a pressure washer. It'll wash the face of this piston perfectly clean. And if you look at all the pistons, one of them looks very clean and the rest of them look dirty, or not dirty, just like this. You know that you have cooling going into the cylinder. And if you have, I wish we had a better example, this particular engine has a lot of issues. If you have only the edges are clean, but the rest of it is not, that is actually the same effect, but of oil. Oil will actually start steaming this and just washing the edge of it. That is called ring wash. That's when the ring is not able to scrape the oil down and it's evaporating here and kind of cleaning this edge only. If you see that, this engine burns oil 100%. Now, how much? That is the question. But if you see that edges are clean, but the rest of it is normal, you're burning oil. Now, let's talk about a few other little things with engines. This is the most basic form of how an engine works, but let's talk about the things you will run into as an average Joe driving your car every day, now that you know more about this engine. Occasionally, you'll drive your car and you accelerate, and you hear this just strange rattling noise, and then it'll go away, sometimes accompanied by smoke. That is called knock, ignition knock, or pre-detonation. Could be either way. Let's talk about the most basic form of that. So we want, now that we understand how this whole thing works, we want that mixture to be ignited for our combustion to start at a specific point. No later, no before, exactly at the right time. As the piston is coming up, we want to ignite that mixture and then push that piston down in the power stroke. If you, for example, have a piece of carbon that got too hot and that was hot enough to ignite your mixture before time, that's called pre-ignition. You're gonna pre-ignite the mixture at the wrong time. So what that's gonna do is gonna cause something like this. It's gonna rock that piston as it's going up because it ignited at the wrong time. And this is where we're slightly gonna go into the fuel conversation. See, engines have a compression ratio. Usually high performance engines will have a higher compression ratio so they can have more power. That's how you make more power out of an engine. Give it more compression, more air, more fuel, either or a combination of. That's how you make an engine make more power. So high compression engines, things are elevated. You have more compression, you have more fuel going in, you have kind of a more aggressive thing is happening. So the temperatures are much higher in a high compression engine on top of the piston and in the combustion chamber than that of a lazy family car that is just meant to drive at normal speeds and we're good. So when you have all that extra heat and you send that gasoline in here, well, if it's too hot, that gasoline will just combust whenever it feels like it because it's simply too hot. And this is where you put premium fuel. So premium fuel, let's talk about it for really quickly here. Premium fuel, it's a more stable fuel. So it will not ignite only from a little bit of higher temperature. You have to have an ignition source. It's more stable. Less volatile is the word for it. So when you have these extreme temperatures because of this high compression and things are on high alert, that fuel will be more stable. It'll be like, no, I will not ignite from this little high temperature. I will wait for that spark plug. But all of a sudden you put regular gas in a car that's designed to run on premium fuel and you will have detonation all day long. And what's going to happen is this will keep rocking and rocking and rocking and rocking. Eventually you're going to wear your cylinder walls and we're going to have major problems. But equally, if you put premium fuel in a regular car, well, the temperatures are low. So fuel will come in, will ignite with the spark plug, and the same thing will happen. I just wanted you to understand why putting premium fuel in a regular car does absolutely nothing but cost you more. So now you know that part. Now, engines do have a protection for this, modern engines. Something called a knock sensor. It's a little microphone, actually. It's nothing fancy. It's literally a microphone. It sits right here. It's actually the place for it in this particular engine. It's listening for a specific frequency that this piston will make when it starts rocking back and forth. When it hears that, it's going to send a signal to the computer. The computer knows, ooh, things are happening at the wrong time. It's going to either back off the ignition timing, which will calm things down, which we're going to kind of ignite later, cool things down, try to lower the temperatures to control this rocking before it destroys things. Now, this happens for a little bit, it's okay. But if it happens all day long, we have a problem. And some cars, you'll notice when they do that strange sound, you'll hear for a little bit, it'll go away, but you feel the car kind of underpowered. Well, why does that noise happen to begin with? Carbon on the pistons and the valves and in the combustion chamber, or poor quality fuel is usually what does that. Poor spark plugs. Spark plugs have a lot of carbon on them and you haven't changed them in a very long time. There's many reasons, but bottom line is you hear that sound, this is not good. You should look into it. Sometimes it's inevitable and it will happen as engines age and everything, but if it's continuous and it doesn't stop, something is terribly wrong and you should look into it. And lastly, I want to clarify one thing. There are two types of things that will rock your piston back and forth. I just want to clarify this because the language can be confusing. You have knocking and you have pre-ignition. Pre-ignition is when the piston's still coming up and you have ignition before it's supposed to happen. That's called pre-ignition. Knocking is when the spark plug ignites the mixture and all of a sudden you have a second ignition from the side. Either it's a piece of carbon that got loaded with fuel or whatever the case may be. That is knocking. Now the knock sensor can pick both of them, but it's really meant to detect the secondary ignition because we're not supposed to pre-ignite on a normal healthy engine, but sometimes you will have that secondary explosion that kind of rocks everything. As the piston now is coming down, you don't want more combustion. All of a sudden that combustion comes up and rocks the piston as it's coming down. We don't want that. Just wanted to clarify the two because they're often confused and they have multiple names with mechanics. So these are the two terms for them and this is what they mean. And this is how a gasoline engine works. Pretty fascinating, isn't it? I've had the absolute privilege of being able to work on these engines for a very long time and experience them. And after some time of working on them, it becomes kind of like the norm. You're just used to it. But every once in a while, we just stop as a new engine it comes out and we're looking into it. We stop and just, wow, things have come a long way with gasoline engines, folks. And it's always fascinating to me, as many thousands of engines that I've been into and working on. It's still fascinating to me, and I hope now you have a better understanding of how exactly these 4 strokes happen and how this beautiful piece of engineering works. Folks, I hope this video was helpful and informative. I hope you learned something new. If you like it, consider giving it a thumbs up. If you're not a subscriber, consider subscribing to the channel. Check out some of my other videos. Until the next video, folks, may the Lord bless you and keep you, and you have yourself a wonderful day. And in case you are wondering, what will we do with this engine after we're done with this video, which is basically a junker, we're going to turn it into a bongo. Listen to this. There you go.